Okay, hello, I'm William. Thank you all for having me here. I work for Erigon, and my talk is about the future of archiving nodes and some ideas on how we can scale state history storage. Well, as you know, scaling is this eternal battle between try to reach users' demands versus increasing limits, chain limits to levels that everybody feel comfortable with. But as you know, scaling is, oops, but there's a lot of chain activity which is based on temporary trends that generates a lot of chain activity for only a short period of time. Uh, However, this data keeps on chain forever. And that's what I'm calling noise in the title of the presentation, but actually I think we could call it junk. So optimizing for junk. The outcome is a never increasing state size, which by itself is a big issue, but in this presentation I'd like to emphasize another aspect, which is the state history size, which affects everybody that serves history as part of their business, like indexers or node providers. Also, it's important to say that the goal of this presentation is not to advocate against history growth, but embrace it and try to think about ways to keep it chain size growth under control long term. So how we can keep size under control? One possible approach is to start looking at real data, real life data, and apply specialized encoders to it. Let me give you two examples based on things that I've researched recently. First, I'd like to talk about index compression. In Erigon, because it's mainly an archive node, we need to keep track of when in the state history some accounts or storage slot change values. This chart shows mainnet data. It's a histogram of how many touches in history given key has. So a key could be an account address, or some storage slot, or a code hash. But you don't need to understand the entire chart. The important thing that I want you to understand here is this blue and red bars. The last bar, the blue and red sections, they represent the amount of keys that have one or two occurrences in the entire history. Notice how they're most of the occurrences inside the Erigon index. And this is how it looks when you take into account the space, disk space. So notice how the keys that only have one or two occurrences, they used to take. This is a previous node version of Erigon, right? So they take most of the disk space, index disk space usage. It gives us an insight that probably there should be a opportunity for an optimization that targets very short sequences. And that's what we did in Erigon recently. We used to use specialized encoding for long sequences called Elias funnel, which is very optimized for, let's say you have a very popular address, or some, for example, a Uniswap liquidity pool that it's changed many times per block. So you need to keep track of all these alter transactions that they change something in the states. But that Elias funnel has some big overhead for very short sequences. So in this case, it's better to just store it for just use a simple array of numbers, and that's what we did. Oops. So we changed our index model to use a mixed strategy. So for long sequences, we still use Elias funnel, but for very short sequences, we just do a simple array of numbers serialization. And that was the result we reached. So we can see that the blue and red sections are now much smaller, and now we have much smaller index size and also faster read access time because there is no overhead into internal data structures just to read the data points. And these are some reference numbers of a recent version of Erigon. Please note how this very simple optimization based on looking at real data, real life data, made us reduce the index size by over half in all chains practically. This is the index compression. I'd like to give another example, which is something that I also have studied recently, which is storage deduplication. One thing I realized while studying chain data is that we have over 10 to 20% of duplicate storage history values. And why does that happen? Well, thanks to standards, in real life data, we have a lot of magic numbers stored on-chain. One, probably the most famous, is this 0xFFFF, which means infinite approval for tokens. And another popular one is you have popular token addresses cross-referenced in between contracts. Which is less common, but also I think it fits in this category of duplicate storage data. This case is interesting because 10% may sound something big enough to be interested to working on and try to optimize, but we actually didn't optimize it yet because in absolute values it's still not much. Compared with the entire size of an archive node, which in case of Erigon is 1.7 terabytes, according to data from September, 2 months ago. But this is something that it's interesting to keep a look at, because maybe, depending on how the chain grows, maybe in a few years, this 10% may represent something very relevant that we could work on and try to optimize and get some very juicy reduction. And in case of Erigon, it would be very easy because, especially in case of Erigon, starting from Erigon 3, we now store all the history in static files. So we could do it very easily by, let's say, reprocessing our historical files, removing this data and changing the indexes to point to this same offset inside this static file. So what is the conclusion of these two quick examples I gave you here? From what I showed you today, I think one possible way to keep optimizing archive nodes long term is to observe real-life data. Based on real examples of try to identify data patterns of used by very popular contracts, it should be possible to craft specialized encoding strategies and keep data small. And also another thing we should try to explore more is exploit immutable data formats, because once you know that data is immutable, it can unlock some interesting strategies, like, for example, the data deduplication that I mentioned. For reference, there is a recent Erigon, there's a recent article I published on Erigon blog, which the charts I used in the first example were taken from here. So there's a more extensive explanation of what they did here. So if you are interested, please take a look at it. And that's it. Thank you very much.